Sejam muito bem-vindos de volta. Estamos caminhando para a última e grande palestra que vai encerrar esse primeiro dia de Festival Futuros Possíveis. Quero lembrar para vocês que tem um podcast do Lab de Tendências nos principais agregadores de áudio. O próximo episódio que vai ser divulgado vai ser justamente falando sobre as macro tendências de 2024 e 2025. A gente começou o nosso dia de hoje falando sobre isso. A próxima palestra, e a última que a gente vai ter hoje, vai ser em inglês. Então, se você ainda não pegou o seu fone de tradução simultânea, corre lá para pegar, para você não perder nada do que vai ser dito aqui. É o clichê, mas é verdade. Vamos fechar com chave de ouro, recebendo o autor do aclamado livro Gênesis, em que ele conta a história do surgimento do Universo. Ele, que é professor da Universidade de Pisa, na Itália, cientista visitante da CERN, Organização Europeia para a Pesquisa Nuclear, e tem o recém-livro lançado Tempo, o sonho de matar Chronos, publicado pela editora Zahara, aqui no Brasil. Inclusive, a gente agradece a editora por ter feito essa ponte com ele. E Guido Tonelli está aqui, diretamente da Itália, vai mergulhar no tempo, essa que é uma incógnita que marca a vida de todos nós de uma forma implacável, independente de quem seja, independente das nossas histórias, o tempo é implacável com todos nós. Quero lembrar que, ao final da palestra, vai ter um tempo para perguntas e respostas, então, de repente, já anota ali a sua pergunta para você não esquecer. Fica ligado na hora que a gente estiver passando o microfone para você poder fazer a sua pergunta. Sem mais delongas, eu vou convidar o Guido Tonelli aqui no palco e agora falando em inglês para a gente poder já começar a nossa tradução. So, I would like to welcome to the stage Guido Tonelli. He's the best-selling author, professor at the University of Pisa, Italy, and visiting scientist at CERN, European Organization for Nuclear Research. You're welcome. Make yourself at home.
Thank you very much, and good afternoon, everybody. I'm sorry, I cannot speak your beautiful language. I can understand when there are slides, as I did it when the previous very nice talk. And today we talk about the same subject that has been covered by other speakers, tempo, time, but on a completely different perspective. You will see immediately. I will talk of time, what is time for science, and you will discover concepts and things that are completely different from our natural, normal perception of time. The story of time is a story of a problem that we have. We have the same problem that we have the old Greeks 2,500 years ago. The myth of Chronos devouring, swallowing their sons is an incredibly nasty myth, which is depicted in this beautiful painting by Francisco Goya in Prado. It's a small painting, but it's horrific. It's really, you see, the tale, the story is that the powerful God was given a prophecy that one of his sons would have deposed him. So that he had to find a way to avoid this end. And since his sons were immortals, they're gods themselves, the only way were to swallow them, to devour them, to eat them. And this is the myth of time devouring everything, eating everything, eating our lives, eating the products of our lives, eating our sons, our creature. It's an incredibly powerful myth which is still valid today. And this issue of time has passed through all the millennia. Leonardo da Vinci called time consumer of things, which is still valid today. Or the intriguing discussion on time by Alice in Wonderland. How long is forever? And the answer of the white rabbit, sometimes just 1 second, which is true in some of our experience. And Emily Dickinson, forever is composed of nows. Again, another important truth to be considered. Up to Roger Waters, to the Pink Floyd, the time is gone, the song is over. So it's something more to say. So time, the reflection on time, has passed through the entire history of humankind and is still valid today. Time is not an issue for scientists. Scientists investigate time, the nature of time, but each one of you has asked yourself, himself, herself, sometime, what is time? How it is flowing? There is no way to stop it, to interrupt it. Is something which is deeply rooted inside all of us. The time that we live daily is something like an arrow that flows continuously in one direction. And it appears to be flowing independently from all events. So this conception of time is the one that brought us here today. No? We have used our watches to organize our time in such a way that we are here in the same place at the same time. And what is the basic assumption? That time flows independently from the events. Today is raining, but time is flowing independently from the weather. If there would have been a sunny day, the time would have flowed exactly at the same speed. No? We don't have any doubts about it. No? Time is flowing and is independent from events characterizing our daily life. This conception of time as an absolute quantity, comes from Isaac Newton and Immanuel Kant, two of the major scientists or philosophers of the 17th century. And they used this concept to create the foundation of science and philosophy. And it's the same thoughts that we still share today. So one of the reasons why it will be difficult, you will see in a moment, it will be difficult for you to master the new concept that science, that modern science is bringing on time, is that in fact you are still, in some sense, we still feel the influence of this golden age, no? That was the 17th, 18th century, in which the concept of time by philosophers or by scientists and the concept of time by artisans or normal people, they coincided. They were absolutely the same. No? And still today we maintain this prejudice. No? I will show you that is wrong, but this is why it's so difficult to win the resistance of accepting another concept of time, because we still are, in some way, heirs of this golden age in which the concept of time shared by intellectuals, philosophers, scientists, and the common people was exactly the same. No? This golden age is over since 100 years, but still the break of this golden age is too recent to allow us to familiarize with the new concept. This is why we have some resistance in accepting the new concept that science has introduced on time. Newton time, the usual concept of time, is valid in our world, in our daily life. No? But our daily life is the life of macroscopic bodies. I weigh 80 kilograms, made out of a huge amount of atoms. Is not valid for bodies that are formed by a small amount, very small number of atoms. So there is a limit in this concept. For those bodies, the bodies which feels the quantum mechanic effects, time is another story. We live on the planet Earth, and our life is confined in a very short, very small amount of, a small region, which is maybe 10 kilometers, on the surface of the Earth. We never go, maybe we can go to the Everest, maybe we can go to explore the outer space, but still we are very close to the surface of the planet Earth, which means that our gravitational field is constant. We have never felt position, situation, movements in which the gravitational fields are completely different from the one that we are experiencing daily, which is the one that it is running at the planet surface, at the surface of the Earth. We don't use to move ourselves at very high speed. No, I'm coming from a plane. The plane goes at 1,000 kilometers per hour. If it is a fighter plane, can go 3,000 kilometers per hour. If it is, I don't know, an astro space ship, a ship for exploration, going to the moon, it will go 28,000 kilometers per hour. But all this speed that appears to be important, interesting, great, are really peanuts with respect to the speed of light. So we are not able to even approach a speed which is similar to the speed of light. And this means that the concept of time we have is completely different from particles, from material components that can move at speeds that are compatible with or comparable with the speed of light. So the Newtonian concept of time works very well for us humans, but does not work for corners which are completely different from our daily experience. So we shouldn't be arrogant. We shouldn't pretend that the same concept that guides our existence, the concept of time independent from any events, flowing continuously, can be applied to an electron moving at 1/2 of the speed of the light, or can be applied to a galaxy. No? The two worlds that are completely far away from our ordinary world, we should accept that in these two worlds, you need other concept of time, another concept, completely different. This is the first act that you should accept. No, we shouldn't pretend extrapolating our experience to worlds that are completely different from our daily world. And this is what has happened as soon as we have been able to explore this world, the world of the microscopic distances, where there are very tiny objects that can move at very high speed. And electrons is very light. An electric field can accelerate him at very high speed. It's very easy to bring an electron to the speed very close to the speed of the light. If you could have had the size of an elementary particle, it would have been normal for us to move very high speed. But since we are macroscopic object, we don't feel this experience. We don't have this experience. The way in which we have tried to explore these two new worlds are completely different and completely independent. I call them the two roads of knowledge. One is the world to which I belong, is the world of accelerators, of elementary particles, of elementary particle physicists or high-energy physicists. I'm one of those. And LHC at CERN is one of our major machines. What we do, we try to understand the composition of the tiniest component of matter. And to do that, we try to produce these tiny elements of matter using collisions among particles. So we try to reproduce in our accelerator the particles that were at the root of current matter and the particles populating the original primordial universe at the very beginning. In some sense, we try to reproduce the conditions of the very early universe. And there is another team of scientists that are astrophysicists, that are astronomers. They investigate the other completely opposite region. They look for the largest possible objects, a star, a galaxy, a cluster of galaxies, the entire universe. We look for the tiniest, smallest possible particles, and they look for the largest possible material structure, like a galaxy or a cluster of galaxies. And their trick is to look very far away. If they look very far away, the speed of light is limited, So you look in the past. So you can go and see the moment in which a galaxy is born, maybe 10 billion years ago. You go back in space, 10 billion light years, and you go back in time. You see events happening 10 billion years ago. No? The two things you see are completely different. We investigate small particles, they investigate large structure. They look back in time and we try to reproduce the smallest possible particles composing the universe. And the funny thing, the important thing, the two things converge. They give us the same story. They give us the same information. And this is a thing which is extremely important for us. Those are the toys that we use are gigantic. We are talking of an accelerator, which is a tunnel, 27 kilometers, in which there are huge, the detector is like a building, four-story building. It weighs like 15,000 tons, like a ship, a cruiser ship. So it is very complex infrastructure. Like very complex infrastructure are the James Webb Telescope or the Planck satellite. The instruments that have been used are used by our friends astronomers. In these two worlds, the very tiny object, the very large objects, time has completely different properties, And this is what we have understood recently. Recently means in the last 100 years. And this is why we still have problems in being used to this new language, to these new concepts. Once we investigate these two words using relativity and using quantum mechanics, you discover things that are completely different with respect to our normal daily experience. In the world of the elementary particles, time behaves in a completely different manner. What are elementary particles? An atom, for us, is a very big object. An atom is 10 to the minus 10 meter. So it's a very small object with respect to our daily life. But for us, this is a huge object because we investigate quarks, electrons, we investigate particles which are 10 to the minus 18 meter. That means 100 million smaller than an atom. So a really tiny object. Are the quarks composing the protons? Are the electrons flying around the nuclei, producing what we call an atom? It's a world dominated by relativistic effect. These particles are so tiny, so small, that they move at very high speed. It's easy to move them at very high speed. High speed with respect to the speed of light, 300,000 kilometers per second, not 28,000 kilometers per hour. A spacecraft, 300,000 kilometers per second. At this speed, there are things happening which are completely unusual. For example, once we accelerate a particle in the LHC, a proton is accelerated in LHC, it is easy, relatively easy, to bring it very close to the speed of light. Not exactly the speed of light, but 99.99999, the speed of light, okay? And what we see, for example, we see something which is completely unusual. Since the particle cannot exceed or even reach the speed of light, what happens to the energy that we use to accelerate him? No? We inject energy, and usually when I accelerate in a car, I see the speed increasing. No? But in this particular system, the speed cannot increase for general reason. No? We cannot exceed the speed of light. So where does it go, the energy that I inject in the system? It goes in mass. You saw? You have discovered E equal mc squared. You have discovered relativity. No? It's very easy. Since I try to accelerate and to increase the speed cannot be increased. And what does increase? The mass. That means the energy and mass are the same things. We have discovered a basic principle of modern physics. Very easy with very simple arguments. And once a particle increases its mass, in this particular case, a proton in LHC weighs 1, use particular, not kilograms, we call it GeV, G-E-V, so 1, no, 1 in some unit. We accelerate it, we increase the speed up to very close to the speed of light, and it weighs 6,800. And the funny thing is that the mass increases, and the time that he lives, that we see from outside, being at rest, we see the lifetime or the time in which the events of the proton happens multiplied by a factor 6,800. Take this example. You have a neighbor which is running daily, no? And running is an healthy activity. And you see that he or she is doing well, is say, fighting aging, because sport is an healthy activity. But imagine if you would see a running person that you live 80 years in average, and he or she can live 80,000 years. You will run every morning, no? There will be no question. In a situation in which individual particles can run at the speed of light, we see their lifetime increased thousands of times, 10,000 of times. Those are not theoretical examples. Many hospitals using radioisotopes use this dilatation of time due to relativistic effect to have these drugs available for exams or for activities. So if somebody is able to move at very high speed, the time as seen by an observer outside the object which is moving, the time is basically multiplied by factors which is 10, 100, 1,000, absolutely incredible, no? If we could run at the same speed, the normal people would attribute us, people not running, a lifetime expectation of 500,000 years. So what happens to the protons, if we could extrapolate to normal human beings, it's impossible for us to run at the speed very close to the speed of light, but you have an idea of the multiplication of the proper time that is happening when objects, very tiny objects, can go very fast. And this is the first thing that we notice, that the flowing of time is not independent from the speed. Now, if you move at very high speed, the flowing of time as seen from an observer outside is completely different, completely different. So we start creating a problem to the prejudice that we had, that time is independent from events. No? You see, time is not independent from the speed. If you run at very high speed, time feels it. And the flow of time is affected. Is affected not for the one that is running, but for the people which are resting, for the people that are not running, that are staying there. Another thing that we notice that space and time are linked, are connected. You see, we are talking of them, of something, there is a relationship between space and time. We cannot talk one or the other independently. And this is something that we have to remember, because it will come again very soon. Then we move to the other extreme. Now we move to what happens to time in the world of the great cosmic distances, the world of galaxy. This is a galaxy which is similar to ours, 100,000 light years in diameter, a huge object. In this world, the same person, Albert Einstein, that developed the special relativity, we were talking about it just a second ago, developed general relativity 10 years afterwards. Is a new vision of gravity, basically. Einstein explains gravity as a geometry effect. Gravity is due to the fact that mass energy distort, curve space-time. Very simple. So you can go back home and I've learned general relativity. Mass energy, curves, space-time. That's it. That's all. The formula is not easy to be explained, but the concept is easy. You see in this picture, which is simplified, because space-time is a four-dimensional object. It's difficult for us to imagine, to figure out a four-dimensional object. This is why you see this sort of network in two dimensions. No? So I put the planet Earth in this network, and this mass energy distort space time. There is a sort of a hole produced in this space time, and if then I put the moon follows the distortion and goes around the Earth. Very simple. John Archibald Wheeler explained it very simply with this beautiful phrase: space-time tells matter how to move, and matter tells space-time how to bend. So matter bending the space-time produced the movement, produced the attraction, produced the gravity. But be careful, no? Because now we are talking of bending the space-time. And you don't bend the concept. You don't bend an abstract element, no? You bend something material. You see, we are coming really to the heart of the question. No? Space-time, space goes together with time, and space-time is something that is very similar to something material. And this is really the new element, the new fact, the new concept that was never imagined in 2,500 years of discussion on time. Nobody was able to even imagine this possibility that time, together with space, is a material component, like this board, can be bent like a piece of wood. Even more intriguing, space-time is bent. That means that time flows different in different gravitational field. At different distance from the planet Earth, there is a different time. So time at the surface, you see, the clock ticks slower and clock ticks faster depending on the strength of the gravitational field. Again, these effects are not theoretical effects, are real effects that are used, by the way, to produce a lot of money, to gain a lot of. For example, whenever you use Google Maps, no, you use a network of satellites that have incorporated these deformations due to general relativity and special relativity to allow you to understand the best way to reach a restaurant. No? Because the precision that you get with Google Maps is obtained because they take into account and they correct for this difference of time between time flowing at the planet Earth and time flowing at 30,000 kilometers distance, where a network of satellites have been launched that allows us to make the triangulation, no? That allows us to find the best way to reach a certain destination. So we are not talking of theoretical effects that have no impact on our daily life. No? The impact is invisible. Nobody knows, very few people know this effect. But, and even Albert Einstein would have been very surprised to learn today, 100 years after his discovery, that we are using his equation to produce a system that allows us to find our friends, or to reach an appointment, or to find for the best route. No? But again, can I go back? The thing that for me makes the things really fascinating is that come back a little bit to Newton and Kant, to this sort of unique Big Bang with this tic-tac. This was the idea. There is still the idea we have today. And then with general relativity and special relativity, this unique clock, huge clock, becomes a myriad of clocks. Each point of the universe has a completely different clocks that runs at a different speed with respect to all the others, because the local deformation is different. And if you want to become crazy, if you wish, each clock has a speed that changes with time, because universe is a dynamic object, is not static. So, for example, in this moment, I have changed the clocks of the entire universe, because I've changed the material distribution of matter in the universe, raising this glass of water. And this fact has been registered by the entire universe. I will never be able to measure it. I don't have the sensitivity to do it. But this is what is happening. The entire universe, you have to imagine this, in which you have a distribution of billions and billions of individual clocks that run at different speed, and they continuously change their speed depending on what is happening in all corners of the universe. I found it extremely fascinating. So, to summarize, space-time is a material substance, can be deformed, oscillates, vibrates. It has a very old microscopic origin, come back to this immediately, contains negative energy, since mass energy deforms it, and we call it gravity. Again, those are incredible consequences of this new idea. The fact that the universe is made out of these two components, mass energy, stars, galaxy, dust, earth, human beings, those are mass energy, but is distributed in space-time. Space-time means that everything is attracted by each other, by every other component. That means that the entire space-time, huge amount of space-time of the universe, is impregnated of negative energy, because once you have bodies that are attracted one to the other, you have negative energy there. So we are close to the conclusion. We have shown, we have collected evidence that space-time has not always existed. There was a time in which there was no time. So space-time was generated together with mass energy. So the two components of the universe, space-time, mass energy, they were born together 13.8 billion years ago. And what do we know about this origin of the universe? That space-time was born from a tiny, almost imperceptible quantum fluctuation of the vacuum. And so the origin of the universe is simpler, is probably the simplest possible explanation we can have. Space-time, negative energy. Mass energy, positive energy. Universe, space-time plus mass energy, zero energy. So our universe is a vacuum state, a state in which the energy is zero. Is a vacuum state that was originated by a vacuum state. So there was no need of energy to produce a universe. Our universe is a free meal, is the huge possible free meal. Contest when you have an economist saying there is no free meal. You can tell him or her, Professor Tonelli showed us that the universe is a free meal. It's a huge free meal, beautiful free meal for everybody. It's a beautiful history is ours. The total energy of the universe is zero, exactly the vacuum state from which it generates. And from the vacuum, you can have this strange mixture of mass energy and space-time that we call universe. The proof of this, that space-time is a material substance, are the discovery of gravitational waves. We saw this material substance oscillating when two black holes collided together in 1916. We saw also that there are corners in the universe, the black holes, in which the curvature of the space-time is so extreme that basically at the center of this strange object, time stops. It loses significance. No? there are places, we have discovered places in which time loses its meaning. At the center of a black hole, imagine one of these huge black holes, for example, the one which is Sagittarius A, you've seen this picture a few years ago, is a black hole which is sitting at the center of our galaxy. It weighs 4 million solar mass. And these 4 million solar masses are sitting just in the center of this region. Imagine the deformation of space-time in this region. Time makes no sense. Times become slower, 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 goes to zero, disappears, basically. So modern physics have found evidence of corners of our universe where Chronos cannot rule. There is no time within, let's say, at the center of a black hole. But these places are so infernal that I don't recommend you to try to reach them. Conclusion, time plays a fundamental role in all fields that physics explores to date, which is 40 order of magnitudes, and still is an indispensable ingredient in describing nature. So we consider it a pillar of our description of nature. And if you like to know more, by tempo. Thank you very much. Obrigado.
A gente vai abrir agora para 10 minutinhos de perguntas. Whoever wants to make questions to you. So, do you have, alguém pode dar o fone para ele?
I can try to understand, and if not, you help me.
For someone to translate the answers for him.
O fone.
A gente vai ter 10 minutinhos de tempo aberto para quem quiser fazer qualquer pergunta para o Guido. Vamos só pegar. Já temos uma pessoa que quer fazer pergunta aqui, mas quem quer fazer? 1, 2, 3. Me perguntaram se eu consigo traduzir. Amor, tem coisa que eu não entenderia nem em português. Sinceramente.
I try. I want to try.
Não sou capaz de fazer isso. Então, eu vou deixar para os profissionais da tradução simultânea. Se fosse qualquer outro assunto, eu até poderia, mas isso, nem em português, eu saberia repetir.
Hi, Guido. Thank you for your lecture. You've been studying time in science for your whole life. I would like to ask you...
Simple.
I would like to ask you, how is your relationship with time?
It's terrible because I'm as you, as it was well described by the previous speaker, we are all slaves of time. Paradoxically, we are trying since ages to master time by measuring it very well. No? And today, we have reached an extremely powerful methods by which we can really measure pieces of time which are really very tiny. You know, the last Nobel Prize was given to a physicist, a scientist that were able to measure attosecond, which is 10 to the minus 18 seconds. And the illusion is that since we are able to measure very well time, we can master it. But the paradox is that in the age in which we are able to produce these incredible achievements is the age in which we are subject to the rule of time in our daily life, probably as it was not in the past, you know, at a level which is impossible to accept. I don't imagine what could happen we're talking of future, what could happen in 10 years or 20 years from now. So we have to do something, because otherwise, once we have sacrificed the relationship, the daily life, and then the sleeping, no? I was told before, even the sleeping is under attack because we spend too much time in sleeping, we spend too much time in curing a relationship with friends, people that we love, our community. So we have to invert this trend. I'm pretty sure there will be. I dream of a new generation of young people that say, "That's enough. Go back."
Olá, vou fazer a pergunta em português, agradecer pela sua palestra, mas uma pergunta bem rápida. Nós Descobrimos muitos elementos químicos.
Espera aí, só um minuto. Se eu for tentar fazer isso, eu vou precisar da sua ajuda. Repete para mim, por favor.
Nós descobrimos muitos elementos químicos.
We discovered a lot of chemical elements.
E esses elementos
And
químicos
these chemical elements
formam o nosso universo.
form our universe.
Eles casam perfeitamente.
They kind of like marry perfectly.
Você acha
Do you think
que existem outros universos
that there are not other universes
que não deram certo?
that didn't work out?
E o nosso foi o único que deu
And
certo?
ours was the only one that did?
Thank you for the question. If our universe is born by chance, through the mechanism that I was describing, from a vacuum state, there is no reason why this event is unique. No? But this is not scientifically proven. It's a conjecture. No? It's an elegant conjecture. I like it. The idea that our universe is not the unique event that was produced in the vacuum state. Similar processes can produce other universes, maybe with completely different laws, completely different constants, completely different evolution. There is a theory which is called multiverse that is very interesting. And frankly speaking, myself, I would consider a fantastic day, the day in which this theory would have been proven correct. But for a theory to be proven correct, we need to find an experimental signature. So this theory of multiverses, some of them hint to effects, subtle effects that we can see at the level of elementary particles or at the level of the great distances, the great galaxies. No? But so far, none of these tiny effects have been measured. That means that still is a conjecture. No? It's an elegant conjecture, but it's not a scientific theory proven by experiments.
Mais alguém tem pergunta? É só levantar a mão ali.
Bem, parabéns pela apresentação.
Congratulations for the presentation.
Nós vimos dois conceitos aqui sobre tempo. Aquele habitual.
Espera aí, moço.
Okay.
Pelo amor de Deus. Eu já estou nervosa de ter que traduzir negócio de física. Eu sou de humana, gente. Já é difícil. Repete para mim, por favor. We saw two concepts about universe.
O habitual do dia a dia.
The usual of our daily lives.
E um ligado a questões das partículas de velocidades muito altas.
And the other one connected to particles and very high speeds.
Nós sabemos que isso acontece, está ligado à física quântica, mas em termos filosóficos, como o senhor entende esse conceito ser tão contraintuitivo? Quer dizer,
essa palavra
counterintuitive.
Moço, faz a pergunta em inglês. How philosophically do you understand time in, say the word?
Counterintuitive.
Counterintuitive terms.
It's a long story that dates back to the beginning of last century when the best philosopher of the time, Henri Bergson, and the best scientist of the time, probably of all times, Albert Einstein, debated together on time. No? A few years ago, I was called to I'm a modest scientist. I'm not cannot be compared to the great giants. But anyway, 100 years after the event, they produced a similar events in which a philosopher and scientist were brought together to discuss time, and I was one of those. And it was an interesting discussion because clearly there is today a better mutual understanding between philosophers and scientists. Philosophers don't question anymore the evidence that scientists have collected on the nature of time in scientific terms, the one that I was describing you in a very short amount of time. But still, there are open questions, open issues. And this we enter, and in this again we enter an area in which there are conjectures. There are elegant conjectures that not been proven yet as scientific theories. For example, some philosophers, modern philosophers, they are very much attracted by some theories. One is the theory proposed by a good friend of mine, which is Carlo Rovelli, together with Liz Smalling, in the attempt of producing a quantum description of gravity. They have developed a theory which is called the quantum loop gravity, that assumes that the basic element is space, a granular space. Imagine space without time. No? In their theory, time is not present as an original constituent of our universe. No, our universe grows on space. Once space is quantized in very small granules that they call loops, quantum loops. Time grows on top of it as a secondary element. It is not disappearing, but is not a primary element. And so we have had a very interesting discussion with modern philosophers. In their view, time disappearing among the basic constituents of the universe, what would be the impact in their view? This is an example of a dialogue that I think is still important and should continue. No? Again, this fact that time is not an ingredient of our universe is a conjecture. I concluded I am against this conjecture because there is no evidence that this is true. Actually, it could be completely false attitude, completely false approach. But it's interesting because it stimulates additional consequences. Because at the end of the day, it's true that we use tools like you were mentioning, which is general relativity, special relativity, and quantum mechanics in particular, that are working very well. In particular, quantum mechanics. If I would switch today quantum mechanics, your cellular phones would be useless, like all the planes, all the cars, all the equipment in the shops, in the companies, in the hospitals, the ships. So the entire world depends on quantum mechanics, even if people don't realize how important is this for all technology that we're using for daily life. But we don't understand it. So we use it, it is perfectly describing what is happening, but we don't understand. And the impression that we have is that there is a sort of surface on which we are swimming, but below the surface there should be something else, something that we don't understand, that could explain phenomena that we follow because should be followed, like the Heisenberg principle, the Pauli principle, the entanglement. There are many principles in quantum mechanics that you cannot violate, otherwise things don't work. But we have not understood from where these principles are originating. So when this happens, usually that means that there is another layer below that we have not yet explored that could explain this principle and maybe could give us access to another vision of time which is different from the one that I have described you before.
Does somebody else, mais alguém tem alguma pergunta? Não? Tem ali, para fechar, é a última pergunta. Vai fazer em inglês, moço?
No, English. Do you think it's going to be possible to travel in time? Well, in theory, I would say yes, but what do you believe? And another point, do you think it's going to be possible to transport between multiverses and different universes? There are some studies in that sense.
Yeah, the first question is easier, although it's not the...
Back, I would like to say back in time, not forwards.
In principle, yes, because there is no, again, depends what does it mean. Because, for example, we imagine you want to see, suppose me, I want to see the moment in which my father and my mother they felt in love, no? Which is, I mean, a lot of time ago. But anyway, how this could happen? It could happen, in principle, this could be possible. I could see it, no? Imagine, again, we are science fiction, no, in some sense, but suppose that there is another civilization which is observing us since ages, from many far away, we are not aware, and they are much more powerful than we are, and they are collecting images of everything, including all our life from far space. They have so powerful telescopes that are able to see our life and to track each individual action once it is not in a house, in the, say, when we are visible from outer space. So in principle, they could have collected this image and they could have access to it. No? It's the same story once I use, which is more serious, I use a telescope and I see something very far away. No? I'm joking on my father and my mother, but I'm not joking if I say that if I use a telescope, I see events that has happened millions of years ago, or billions of years ago, or 10 billions of years ago. No? It's the same trick. No? Once I talk of my father and my mother, people tend to think it's impossible, is a joke. But if I talk of a modern telescope that gives you the beautiful pictures that are coming from the James Webb telescope, you see galaxies or stars that, as they were billions of years ago. So you're actually doing exactly the same. A thing that you cannot do, you cannot go in the past, at least for the moment, I cannot exclude. It will happen sometimes. But there is really a problem, no? Because it's the principle of causation, which is under scrutiny. No? Suppose that I could go back in the past, again to the scene that I was describing before, and I see my father and my mother, and I jump among them, and I try to break this tie, this relationship, by some means. No? Clearly, this is impossible, because this means that I would create a contradiction with the fact that I would not be here, no, if they would have split when they were young. No? So it is impossible to break the principle of causalities, but it is possible to have information. This seems to be not violating basic principle. Then it is possible to go in the future, which is, again, easier, quotation mark. Going in the future means you have to move very fast. The fact that we are not able to reach the speed of light is a technical problem. It's not a scientific problem. No? So we are here in the year 2023. I would be surprised if in the year 3023 the same limit will be still there. No? So imagine centuries from now, there will be somebody, some young girl, maybe inventing a way in which we can use ships, astro ships that can fly at half of the speed of light, or maybe 90% of the speed of light. Consider also this, that if you are able to do it, and it's a matter of trying to find the right combustible, the right way of producing energy. So there are ideas also there. It's not a completely useless activity. Then time for people that will stay here on the planet Earth will flow at the same speed. But time for the people that will be on the ship, on the spaceship, for them will be exactly the same. But actually, if you go to the speed of light, take a photon that is coming from the cosmic microwave background, has been emitted 380,000 years after the Big Bang, and then you capture it. But if you could talk for him, the time is zero. I would ask, what have you seen in this last 13.8 billion years? And he said, but I've just been emitted. You capture me immediately. For an object which is moving at the speed of light, time is zero. Time is nothing. Time is basically inconsistent. No? And so for people in the spaceship flying at 90% of the speed of time, they could reach very far stars, for example, because for them 1 year would correspond maybe to 200 years on the planet Earth. Or you can reach, as in the movie Interstellar, you can imagine you can reach a region very close to a black hole, away from the dangerous region, but close to the horizon of the event, in which time is flowing so slowly that once you come back on the planet Earth, it is 50 years or 100 years in the future. So all these are scientifically, this way of, let's say, flying in time, backward, in the sense that I was describing before, or forward, using these two phenomena, can be scientifically explored. No? It's just a matter of technicalities, technologies that we have to develop to make these things that today appears to be impossible to be realistic.
Thank you very much, Guido. Right on time. Thank you very much.